All right. Okay. Good morning, everyone. So let's focus. So today we should finish the last two topics to actually make us able to analyze any electric circuit as basic as it gets in grade 11. So as you can tell, on each desk there's a something with that says DC volts on it. This is what's called a what? Voltmeter. This is voltmeter. They come in different shapes and sizes. This is one. This is one. Yeah, absolutely. Yeah. This is one. We're gonna actually use it to. There's another one. Where is it? Ah, we also have these sometimes, or we also have these ones. And these ones are what? Voltmeters. These are called because these actually measure more than one thing. So this only measures voltage. The only thing that this measures is voltage. This measures voltage, this measures current, and this measures resistance. Okay, so this is called a multimeter. Multi because it does multiple things. But is this one analog or digital? This one is digital. Okay, these ones are analog, so you have to actually watch out how the needle goes. Okay, this one just gives you a value, and you just record. Okay, we don't have many of these. I think we only have two. But honestly, I like using these more. Okay, they're just more easier to connect, and they actually show physics at the most basic level. Okay, so remind me again, what did we do yesterday? Come on, we did two topics. Yesterday we did two topics. What's up? No, that was the day before. Electric charge was a full day on Tuesday. What did we do on Wednesday? Not that's today. What did we do yesterday? Yesterday we did two topics. Nope, we didn't do circuit. We did not do circuits yet. But what's the equation? No one's opening their notes except for Tammy and Maria. Come on, what did you do yesterday? Two topics. Current, that was the second one. What was the first one? What was the first topic we did yesterday? We did two topics. No, there was one before it. Electric force. And electric force had the same equation as what? Almost the same equation as gravitation. So it's very easy to manipulate the exact same mathematical way. Electric current. How did we define electric current? What's the word current? Forget electric. The word current means what? Flow. Flow of electrons. So you only get what? You only get current when electric charges are in motion. In motion, exactly. So today we do what? We do what's known as potential difference. Potential difference. This is just the fancy name of what? Fancy name of voltage. Fancy name of voltage. So go ahead. So whenever we connect anything in a circuit, absolutely anything, even if you yourself touch something that's actually connected to an electric source, you just created a what? A circuit. Okay. So whenever you create a circuit, some electrons have to be moved around the circuit. Some work or energy must be involved. Okay. Some work or energy must be involved. So right again, what unit are we revisiting now? What unit are we going back to or relating electricity to? No, what unit? Work, and we're going back to work and energy. Not too much, just for today. That's it. Okay? Work, work, work. Work, work, work. Honestly, man, never grow up. Keep that child inside. Okay? So what's the best way to define potential difference? Question for you yesterday. Do you remember how I showed you on the app, on the website, how the voltmeter had to be connected with how many leads? With how many? With two prongs, with two hooks. When we just connected one or touched one, did we get any reading on the voltmeter? No. So that means what? You need always how many? Two. That's why it's called what? Potential what? Difference. You need a difference between two physical points on the circuit. Okay. So one way to define it is, or the way to define it is the work slash energy. This is not division. This is not a dividing sign. This is just the work slash energy involved when a test charge. Okay, just so you know, I'm just using the word test charge because the word test charge is actually very important in grade 12 physics. Okay, in grade 11, just call it a charge. Just call it a charge. A test charge is moved from one point to another point within an electric circuit. Okay, that's the definition of a what? Of potential difference. Potential difference between one point to another point is how much energy was involved to get it from point A to point B. From point A to point B. Okay, it's like you're trying to answer the following question: how much energy or work is associated with physically moving a single charge? How much of a charge? I don't know. A microcoulomb, 3.5 millicoulombs, a single electron, 20 electrons. I don't know. Just a charge, just a sphere with a charge from one point in space within a circuit to another point. That is the definition of potential difference. Okay. So I told you that potential difference, listen up. I told you that the word potential here is just a fancy name for which word? What does this measure? Voltage, exactly. So everyone, I want you to, above the word potential, write the word voltage. I'll write it with you. Okay? So write the word voltage. VOLTAGE. Okay? So you can either call it, everyone, you can call it one of three things. You can call it what? Potential what? Or you can call it what? Voltage difference. Or just call it what? No, voltage. Almost no one says what? Voltage difference. Almost everyone says just what? Voltage. But it's always known to be what? A voltage what? Difference. Because again, how many hooks do you need? You need two hooks, which means you need a difference between 2 points. It's kind of like saying force is what? Is a vector, but you never treat it as a vector. You just treat it as a what? As a scalar, but you know fundamentally it's a vector. Same thing with this one. Potential or voltage are always a difference between 2 points in space. Okay? But no one says difference. We understand. Okay? All right, so let's go next slide. Okay, what do you think, everyone? What do you think the difference? Sorry, I mean the symbol for voltage is small or capital? Now, we already used small v. What was small v in all of kinematics? Velocity, or as a scalar, speed. In capital V. Capital V, everyone. Capital V in all of physics, almost all of physics, is what? Is, no, capital V is voltage. How about in math? What's capital V? Come on, 3D, volume. Volume, perfect. So the difference is, but because it's a difference, technically it has to be what? Delta V, because you're touching 2 points and you're measuring the difference in energies between the two. Okay? What can you tell? Positive, sorry, scalar or vector, just by looking at it. Scalar. What do you want to say? Baha, you had something. Something final minus something initial. Absolutely. It is okay. Okay, it is the same thing, but we're gonna skip the what, the final and the initial in favor of what, an easier equation. But no, not even that. I'm gonna give you the equation without having to do what, the final minus the initial. You see what I mean? But you're right. It is fundamentally what, a final and an initial, or an A minus a B, or a B minus a, depending which point is first, which point is last. Okay, question for you, everyone. Is this a scalar or a vector? Okay, how about the sign? Could this be positive? Any delta generally could be what? Positive or negative or zero if the two values are the what? Are the same that you're subtracting. Nice. So go ahead. It's yeah. Uh, and you're gonna see today that when we connect this to the what? To the voltmeter, and we switch the terminals, the needle will want to move which way? The other way, because now the electrons are forced to what? To loop in a completely different. Yes, you're right. So remember, electric potential difference is a scalar quantity, although it could be positive or negative or zero. And another name for potential is voltage. We already established that. So you can also call it voltage difference, or just call it voltage. I bet you can never talk to an electrical engineer and they would keep saying what voltage, what difference. They'll just say what? Voltage. Yet they know you need how many hooks? Two hooks. There you go. What's up? Exactly. You need two hooks because the electrons have to move from one point to another point. Okay, we're good? Okay, all right. Come on. What's the unit of voltage? It's the only, I think it's the only thing in physics that the name and the unit are the same. Voltage is measured using volts, capital V. So the standard physical unit of electric voltage difference is called the volt, symbolized capital V, because it's actually what? It's actually a name of a person, an Italian physicist, Alessandro Volta. Alessandro Volta, Volta. Yes. Alessandro is the Italian way of what? Of Alexander. Alessandro is Alexander in Italian, like Alessandro Del Piero. Okay? All right. That's it. Capital V. Okay. What's the mathematical formula of electric voltage difference? Okay. Now, what was the definition I gave you? Read the definition on the first page. What's the best way to define potential difference? Perfect. Well, hold on. You said what? Work slash every time we talked about work and energy, I always had to give you how many equations? Two. One with the work symbol and one with the what? With the energy symbol. Like when I gave you power. What's the definition of power, everyone? Come on. You can say it in two ways. What's the difference? Sorry, delta E over delta T. That's one way. What's the other way? Work over time. You always have to show it in two ways because you're using two different concepts. There we go. So go ahead. Work involved when a test charge is moved from a point to another point within an electric circuit, or energy involved when a test charge is moved from one point to another point within an electric circuit. So, since work done and energy used are the same thing, we have two mathematical definitions for electric potential difference, just like we did for power. Just like we did for power. Also efficiency. Everything that depends on work also depends on energy. So you always get two equations. They are really the same, but technically you have to be given two. Okay? All right. What are the equations? Here they are. Voltage difference is either work done when moving a test charge divided by the amount of that test charge over voltage difference, sorry, energy associated with moving a test charge divided by amount of test charge. Question for you. Do you think signs matter here? They do. All of these signs matter. The sign of this guy, 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 and this guy, and this guy. That's why I told you potential difference could be negative. If it could be negative, that means what? Potentially this one could be negative, as we know from the cosine theta back in the work and energy unit. And this one could be negative because your energy final could be less than your energy initial when you do EF minus EI. Okay, so all signs mandatory. By the way, this, just so you know, uh, in grade 12, we really go deep into it, into the sign analysis for this. But in grade 11, everything will end up being positive. So don't worry. But in grade 12, things might end up being negative. Because, by the way, in grade 12, we don't do circuits, just so you know. Circuits is an interesting concept. You do it in grade 11. You don't even talk about it in grade 12. Yet when you go to first year, after technically basically 1 year of grade 12 not seeing circuits, you see circuits even harder than you see them in grade 11. It used to be in grade 12, and 15 years ago, they took it out of the curriculum. So now you don't see it for a full year. And yet, you jump to it after first year, or into first year. Well, I was not consulted when they changed the curriculum. But the good news is, if you're well-founded now, you can always go back to my notes and have a quick refresher. Q what? What Q? Oh, okay, everyone. Ali's saying, should this be uppercase Q? Remember, you have complete freedom in choosing what the symbol for charge. You can say uppercase Q or lowercase q. Up to you. Nope, absolutely not. Just like heat, okay, capital Q or small q. All right. Okay. By the way, everyone, do not care too much for the word test. Test charge is any charge you plant in a system and see how the system is by watching how it moves. You're testing the system by seeing how it moves. It just means an electron or a charge that's moving in the circuit. Don't worry too much about it. Do not worry too much about it. Okay. All right. Next slide. Okay. Okay. That's the definition of a single volt. A single volt means what? Means 1 single joule of energy to drive 1 single coulomb of charge. 1 to 1 to 1. So let's actually do the 1 to 1 to 1. 1 to 1 to 1. So, for example, what does it mean if I told you that this battery right here, what's the voltage on this? 6V. Can someone tell me what does 6V mean as far as those two numbers are concerned? This is a 6-volt battery. So this number is 6. What does this mean? What does it mean with these two? Is it 6 divided by 6? 6 divided by? So again, because if this was If this needed 6 joules of energy to drive 6 coulombs of charge, it would be 6 divided by 6, and it would be just what? Which means it should say, where is it? 1V on it. But it doesn't say 1V, it says what? It says 6Vs, which means this one is 6 and this one stays as 1. Nice. This battery requires 6 joules of energy to drive enough electrons to make up 1 coulomb of charge. Okay? In other words, how many joules of energy you need to push 1 coulomb of charge. By the way, if I actually, you know what? We should have done this the first day when we talked about the electric charge. Does anyone know how many electrons do you need to pile up to collect 1 single coulomb of charge? Think about it. How many small electrons do you need to pile up in a ball? Oh, great, but give me a number. There's an exact number. How are you going to figure that out? Which equation are you going to use? I'm asking you to build up to 1 coulomb of charge. And I'm asking you how many electrons do you need? Which equation do you use? Q equals NE. Everyone, let's do a quick calculation here. If I want to do, don't write it up. I just want to tell you. So if Q equals NE, how do you rearrange this? Come on. N equals Q over E. Okay. How much charge do I want to build up to? 1 single full coulomb. So 1 divided by, hey, what's the magic number for a single electron charge? 1.6 times 10 to the negative 19. All right? Go ahead. Divide 1 by that number. Come on. You can use the X notation or the brackets. Up to you. We are, as Bahat said, we're expecting an astronomical number. So Q is the charge in coulombs. N is just the number of individual electrons you need to collect together. And E is the single electron charge. 1 single contribution. 100. It's the concept of the universe. All electrons in the universe are identical twins. How much? Yes. 6.25 times 10 to the 18. You need, if you're driving, everyone, if you have 1 coulomb, look at me. If you have 1 coulomb of charge moving in a circuit, moving in this wire, for example, if you have, someone tells you there is 1 coulomb of charge moving along this wire, they're basically telling you there's how many electrons? 6.25 billion electrons moving what? Moving what? Together in the what? In the wire. 1 coulomb is equivalent to what? 6.25 billion electrons. Is it making sense now? That's what they say, or that's what they mean whenever they say 1 coulomb. A collection of 6.25 billion electrons. I just want to say. Okay. So the definition of a volt is what? It's the volt is the amount of potential difference between 2 points when 1 joule of work needs to be done to move 1 coulomb of charge between them. So whenever you connect your hooks and it reads 1 volt, you know this circuit burns 1 joule of energy to move 6.25 times 10 to the 18, or 6.25 billion individual electrons from that point to that point. By the way, yesterday when I moved the hooks to another 2 spots, did it stay the same or did it change the number? It changed the number, yes, because the energy here minus the energy here could be potentially different, just so you know. So always know where to hook. We're going to see that today. Actually, more tomorrow, but a little bit of it today. Okay? Is there another? Yeah. Hey, we can flip this to define a joule. The joule is the amount of energy or work that needs to be done to move how much charge? 1 coulomb of charge between 2 points of space that have how much potential? 1 single volt. Is this already done for you? Okay, awesome. All right, let's do a couple of quick demos, I guess, or so just one. All right, go ahead. So a computer processor chip transfers or burns or needs 120 joules of energy while moving 52 what? Yeah, I will never tell you 52 coulombs of electrons. I'll tell you 52 coulombs of what? Charge. I either give you the number of electrons or the amount of charge, but I'll never give you an amount of electrons. No, I don't think that makes sense. Okay? Calculate the electric potential difference of the chip. Okay, question for you. How many hooks do I need to measure any voltage? So everyone, I just want you to sketch a small, how does a computer chip look like? Kind of. Yeah, like a thin what? Thin wafer slice? Yes. But with what? With two what? With two terminals coming out of it, okay? To connect to the what? To the rest of the motherboard, for example. So I just want you to sketch this. Basically, like a thin wafer chip, and then what? A lead coming out of here, and a lead coming out of here. Okay, oops, sorry. No, no, no. No FBDs are required for this unit. Nope, I don't. Sorry, I don't think so. Nope. Not for circuits. For next year's what? Effect of electric fields on moving charges? Yes, because an electric field could push or pull a charge. Okay? What do I want you to do now? Okay, everyone, look. Make a circle with a what? With a V. Make a circle with a V. That's gotta be our what? Our voltmeter. And then just what? Come up with a lead and connect it here, and come up with another lead and connect it here. The question is simple. What reading would you get with these two numbers? That's it. All right. With the amount of energy transformed and the number of or amount of charge moved through. Okay. What was the equation now? Delta V equals what? Do you divide the charge by the joules, or do you divide the joules by the charge? Yes. So you divide 120 joules by 52 coulombs. How much is that? It's between 2 and 3. It doesn't make it to 3. So that means, is it 2.3? 2.2, give me one more digit, because technically we have to go to 2 decimals. Sorry, 2 sig figs. 2.3. So 2.3. In what unit? In volts. That is what you're going to see here. That is what you're going to see here. Okay? So charge is, okay, electrons are the ones that build up charge. If you collect more individual electrons together, that means what? You're collecting more charge. Uh-huh. Positive if you steal electrons, negative if you what? If you add electrons. Okay? Okay, what I want to give you now is what? So far, yes. I want to give you what? Some batteries. Before we do any electricity experiment, what do you always have? Do we always have to? Do we always trust that this is 6V perfectly? No way. They've been sitting in a box for like maybe 3 or 4 years. They've been what? Slowly what? Depleting and degrading and just corroding on the inside. Okay. So what I want you to do is what? I'm gonna give you. I'm gonna actually give you. Go ahead, pick one. The first thing we always have to do is actually see what kind of a charge, or sorry, what kind of a voltage. Yeah, go ahead, pick one. لا خدها خليها عشان نكون بس وجه بعض. Thank you. Mhm. Okay, does every group have one? Okay, what do you get now? You need what? You need 2 wires, just 2. Okay, you got 2? You got 2, okay. Here's 2. Here's 2. Here's 2. Here's 2. And here's 2. Okay, hold on before. No, no. Before we do that, okay, what do we always need to do? Every battery has how many terminals? 2. One is always what? And one is always what? One is positive, one is negative. What? Okay, look at your voltmeter. It already has what? One lead with what sign? Positive, and one lead with what sign? Negative. Okay, no, no, before you connect, everyone, no, no, Ali, wait, before you connect, hold on. What are we expecting this battery to be? I mean, we're expecting it to be what? Around 6. Okay, do you see those numbers here, everyone? Look, See, those are the what? Those are the scales. How do you read it off? Okay, we know that our maximum, well, our maximum for the battery. So what maximum scale should I get from here? Do you think if I use a scale of 1, is that big enough? 2.5, 5. No, again, unless I know it's really depleted to be less than 5, I can choose the 5. But I don't know that's gonna be 5. It could be what? 5 point what? 5.8, right? So I need to go higher. What's the scale higher than 5? 10. What if you go 25? Could you go 25? Yes, but that means what? Your needle is not gonna what deflect as big as it could. It's gonna deflect what? Less. Okay, question, everyone. Question for you. What if you pick a scale of 1? What do you think the needle is gonna do? It's gonna what? It's gonna deflect and even go because it wants to what? Go to more than 1. So see, I don't know. That's the thing. Go ahead, put it on 10. Go ahead, put it on 10. But before you connect, put it on 10. Okay? And now go ahead. Okay, everyone. Did I give you wires? No. Oh, okay. Everyone, how do you connect wires? Look. Everyone, eyes on me. Some people connect it this way. Look. By the way, do you know what we call these? Nope. No. This is the wire. What do they actually call this clip? Alligator clip. Because seriously, this is the actual scientific into alligator clip. So everyone, look. Some people do this. Come on, connect. Go ahead. Some people do this. Look. Look. I'm not a fan of this. You know why? Because it's touching the what? The plastic part. I'd rather what? Unsmith it all the way and then what? Connect metal to what? Metal to well. Okay, and then here you can connect this any way you want. Go ahead. Go. Yep. Yep. Make sure you go positive to positive and negative to negative. Okay, so you connected negative to negative. Okay, come on. Next one. I remember the spark yesterday. Yes, because this already has a resistance in it to what lower it down a little bit. Oh, really? Yes. Everything has to be designed with a resistance to make sure it doesn't fry. Yeah. So, what values are people getting? Oh, okay. Hold on. 1 second. Everyone, just so you know, Yasmin, just look. I tested all of these voltmeters before, and they work. Yet, this one's. Oh. Maybe you should. If maybe it's a faulty there, but the voltmeter should work. I don't think it's a wire problem. Wires are decent. Minus is going to minus. Interesting. Okay, let me try another battery. So positive to positive. No, other way. What the? No way. Positive is red. Oh, maybe it is the wires. Okay, let me see if I can get you. هذا خربان. لا مش خربان. I tried all of them. قبل ما تيجي على طول. All of them. This is the second battery. What second? Plus the plus. One, the second battery we changed it. That makes no sense. Is anyone's okay? Who is it working for them? Okay, 6. Working? Work? Okay. Could it be the wires? Oh man. Okay. Who? Okay. Did it work? Okay. Give me the wires. Let me check. Yep. Just unhook the wires. Yep. Yeah. The wires. Yep. Yep. Sorry if I'm relaying that. No, it's weird. I tried. I'm pretty sure the voltmeters work because they work before. Okay, let me just try here. Okay, so hot minus. I'm gonna put plus. Yes. It doesn't matter. Doesn't matter. Usually people are like sometimes like it's black and red usually. Yep. Yep. It's the wire. Yeah, I have to make sure that I have good wires before Monday experiment. Okay. Yeah. Okay. Okay. That's fine. Okay. That's fine. Perfect. Okay. Okay. Question for you. Flip it. No, no. Don't flip this one. Don't flip both. Flip this one. Flip just one end. Yes. Yeah. 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 No. See what's gonna happen. Check. Yeah. See, it wants to go to 6.5 the other way. That's why you always connect what? Positive to positive. Perfect. Okay. So, yep, unhook. Fellas, unhook. Okay. I'll go to the other two groups. All right. All right. Okay, it's not. Okay, so go ahead. I know, positive or negative, whatever you want. What'd you get? Positive. Okay, so this one goes to positive, and this one goes to negative. Sorry, oh, no, no. Positive to positive, yes. Negative to negative. There we go. Very close to what? 6. Very close to 6. Awesome. I want you to flip. Either flip those two or flip those two. Do you see how it wants to move the other way? If we had what? If we had a 0 here, it would have moved this way for one setting and this way for another setting. You see what I mean? Some devices have the dial with a 0 in between, with positives on this side and what? Negatives on the kind of like what, an x-axis. This one has the 0 where here. So if it's gonna move, it's either gonna move here or here, but it doesn't have any space for it. Perfect. Yep, that's all. Just a bit confused too. Okay. Okay, let's go. انتوا واز ما اشتغلوش صح؟ No, okay, all right. Go ahead. Yeah, positive. It doesn't matter. Absolutely. Color has no relevance to the whole thing. معلش, it just. So this is what? Minus, okay. Put the minus. Yep. مريم, put the plus. Okay. Yep. And then. Mm-hmm. Try. I'll just try this Barry. Okay. So negative to negative. Negative. There we go. Okay. Why did it go beyond? Because my scale is set to what? 5. It's too big. It's too small for it. Good enough. Good, but yes, as much as possible. Okay. Now I want you to either flip these two or flip these two. Go. Go ahead. Not as you wish. Doesn't matter. Grip, grip. All right. Push in. All right. Look what's. See, you just you didn't even need to clip. Just touch it. Just Just touch it. Just touch it. It wants to move, but where? To the other side. Everyone, look. Eyes up here. Look. Some voltmeter and devices in general. Yours, where does it have the 0? In the middle or one of the sides? Yours have the 0 here, and let's say 100% here. So that means what? But some of them have what? Have the 0 where? Here, which means here's what? Negative 100%, which means here, if you connect it one way, how is the needle? But okay, if it's not connected, where's the needle exactly? In the middle. In the middle. If you connect it one way, how is the needle going to move? This way. You're going to see it move. And if you connect the other way, it should move exactly the same amount, but which way? That way. But our case, or our devices, have the 0 where? On this side, on one end of the interval, which means what? It one way, let's say 10V, one way it's going to fully move this way, and the other way, you see it just what? It wants to go down to what? To the exact same amount, just the other way, but it can't. Because what? It's restricted. Is it making sense? Like the spring in it does not allow it. Okay? And that's basically how we use voltmeters, okay, to just measure how much battery voltage we have to start the experiment with. Okay, awesome. That's all we need to know about voltage on its own. The next one, electric what? So that would be okay. If we've covered electric resistance, then we would have covered how many things? The three major things of circuit: current, voltage, and what? Resistance. Every circuit is these three things. Okay. Okay. All right. Shh. Focus. Focus. Come on. We can finish this in the half hour. Now, what did I tell you that the word resistance in electricity resembles a word in force? Friction. Every friction is what? Minimizable, but you cannot what? Eliminate. Same thing with what? Resistance. Has anyone heard of, okay, before I even keep going, question for you. Has anyone heard of something called superconductivity? Superconductive. So apparently, okay, let's think about this for a second. Um, if you heat something up, everyone, if you heat something up, what are you doing to the motion of electrons and particles in general inside of that material? Are you making them vibrate less or more? Okay. So imagine now that the particles inside of this wire, everyone, listen, imagine if this wire is 5 degrees hotter, still solid, but 5 degrees hotter. Okay. And then it has its own electrons, right? By the way, what could it be made of usually? Copper, maybe let's say copper. Okay. Old ones are copper. Okay. So this copper wire has already what? Has already electrons of its own, ready for what? Ready for being what? Pushed, like pushed to what? To make a current. Then you what? Then you push what? Energy through it. Now, if you heat this up and the electrons are moving a lot, is the energy going to be going swiftly and smoothly in or bumping into a lot of electrons? So that means what? If you increase the temperature of a material, does it still have the same resistance or a different resistance? Exactly. Do you see what I mean? So what things affect resistance? Apparently what? Heat and temperature. Also what? Type of the material. Also what? The density of the material. And so many things, okay? We're not going to talk about these, but I'm just trying to tell you what resistance is, okay? So every material in the universe has its own resistance. Can two different materials have the same resistance? Can two different materials have the same atomic number? Can two different materials have the same index of refraction? Nope. When they classify materials or when they characterize them, one of the things they could actually measure to make sure they know which material is its electric resistivity, if it conducts electricity. Can you ever identify polymers by their electrical property? Are polymers insulators or conductors? Polymers. Yeah, they're full of carbon. They're very weak conductors. They conduct, but very, very, very small amounts of electricity. Okay. Polymer. So polymer is any molecule that's basically what carbon based as a chain. So whenever you talk about petroleum engineering, yeah, crude oil, basically like this is a polymer. This rubber right here is a what? Is a polymer. Polymerization is the process of what? Connecting so many carbon chains together. That's polymerization. Okay. So every material in this universe has resistance, no matter what state it's in. Even gases have resistance. It's just very, very, very small. Okay, gases has it, solids have it, and liquids have it. Okay, just like friction, you can never eliminate friction. You can never eliminate resistance. Why? Because you can never eliminate electrons. What of the material itself vibrating and actually what obstructing current going through. Okay, resistance is simply due to the what interaction between the molecules of the material, and the passing electrons. The wire material resists the motion of electrons, leading to energy loss within the wire. Touch any wire after a while. What does it feel? It never feels cold. It always feels what? Hot. Again, I told you, just like friction, right? What is the most common energy that you lose friction to? Thermal energy. Same with what? Touch any wire after a while, especially if you have a bad what? How many people have like a bad charger or a bad adapter that heats up very easily, especially the old one? Exactly. Yeah. Because the electrons are what are interacting and losing so much energy to the wire material due to resistance. Okay, we're good. All right. So let's read this quickly. So yes, if you ride your bike down a smooth road and then through some mud, you would immediately notice that it's difficult to maintain the same speed, i.e., you have friction. you would experience a resistance to your movement. In a similar way, all matter has some resistance to the flow of electric current. It's a measure of how difficult it is for current to travel through a material. Some materials have a high resistance. High resistance. That means what? They are insulators. High resistance means you're not letting current go through, or you're letting it, but very, very, very minimally. So insulators such as plastics or polymers, as I explained to Ali, and rubber have high resistances. Other materials have what? Low resistance, or they like to call it high conductive, highly conductive. Um, they allow electrical currents through them more easily. What usually have high conductivity? Metals, okay? Iron, copper, all of that. That's why you never make a wire out of what? You never, but okay, you never make a wire out of rubber. But why do you encase it in rubber? So you don't touch what? It's no actually it's actually known as a naked wire. If you actually touch the what? The copper itself, that's it. You're electroshocked. That's why this is just what? Just to make it. You know what? Have you ever? Okay, how many people studied biology here? Biology. Okay. Do you know what surrounds your nerve cells? A nerve cell is a very long cell. Okay. Of what? Of an electrical impulse traveling through. What's surrounding it? Well, not rubber, but a sheet that what protects it and what increases the what? The speed of signal as it goes through. Has anyone heard of a disease called MS? MS, multiple sclerosis. So MS is basically a disease that it's known how it happens. It's just not known why. MS is a disease where people with what? With certain in their nerve cells. The problem is everyone look, the rubber sheet around it is decaying. What does that do? Two things happen. The nerve cell is not protected anymore, or not as much. Also, this rubber sheath actually what increases the what? The speed of the signal. So if it decays, what's going to happen to the speed of the signals? Slows down, or even what? Completely diminished. Which means what? The brain and the spinal cord is trying to send signals. The problem is they're very diminished. They can move, but they have what? Very weak mobility. They get tired easily because they can't just what? Send signals as efficiently as someone with a what? Full sheath around. Okay? All right. Come on. What do you think the physical symbol for resistance is? No, you're giving me the unit, my friend. I need the symbol in the mathematical equation. What? R. Do you think it's capital R or small r? I've seen it mostly, I've seen it both, but I've seen it mostly what? Capital R. Capital R. Okay. So the physical definition, sorry, symbol is capital R. Again, can you ever get negative resistance? What do you think? No. Resistance is a what? Is a physical measure of how hard it is to pass electrons through. You cannot have it negative. Theoretically speaking, what's the lowest resistance you can get? Zero. You can never go lower than zero. Yes. Okay. And it has no direction because the current has direction. Resistance has no direction. It's just the what? It's just the actual resistor itself. Okay. All right. You got this one. What's the physical unit? Ohms. Yes. OHM. George Ohm was an influential German physicist who was the very first one to actually what? Discover the relation between the three major players: voltage, current, and resistance. By his discovery of resistance and really understanding Ohm's law, finally circuits became its own field of study. Okay? Standard physical unit of electric resistance is called the ohm. And it's okay. What is that? Does anyone know what this one? It's a Greek letter. What? By the way, I'll give you a hint. It's actually the name of this Greek letter is what? Is a name of a very, very famous, luxurious watch brand. Omega. You got no? You got the what? Omega. Okay? Or in the words of James Bond, Omega. Okay? How do you sketch the symbol? I like to call it the keyhole symbol. I don't know why it looks like a keyhole to me. Just do this. Look. That's it. You don't need to make it fancy like this. No, keep it simple. That's it. A what? A squid? Great. I don't know why. The first time I ever saw it 25 years ago, looked like a keyhole. I don't know why. I'm not sure. That tells you something about how I see keyholes. Okay? Omega. That's why another name is what? Ohmage. So remember now, voltage from volts, amperage from amperes, ohmage from ohms. Okay? Oh, sorry, my bad. Current is measured in ampere, and another name is amperage. Potential is measured in volts, and it's called voltage. resistance is measured in ohm, and it's called ohmage. I just find it easy way to remember. Okay, everyone. I really don't care which ones you use, but if I ever give you like a fill in the blanks, I would rather use what? These. The only one I'm willing to substitute from these here is what? Voltage. Okay, almost no one says potential. Everyone says voltage. But I don't want you to say amperage or ohmage, current and resistance. Okay? All right? Ladies and gentlemen, the most important equation of what? Of circuits. This is what you talk to an electrical engineer, you tell them, hey, I know what you spent 4 years doing. I could have taught it to you in like 5 minutes. That's it. Everything revolves around this equation. The voltage across a certain section is equal to the current through that section times the resistance of that section. V equals IR, the most important fundamental cornerstone equation of electrical engineering. 4 years they spend just trying to really understand circuits using this one. At the end of the day, they just want to know if the voltage is not high enough, so the current is not enough to what? To burn or to fry the circuit based on the resistance. Again, the triangle works for what? Anything that is the what? The multiplication of two other things. Every time. Yep. V equals IR. V is the main one, so it's here. I and R are the two equal player. You want one, you hide it, and you just see do whatever the math tells you. Okay? All right. Now, before we do, what do we have next? Okay. So the definition of the ohm is the following. There we go. A single ohm means a single voltage was measured over a single ampere. That's what it means. So I'll do the 1 to 1 to 1. 1 ohm means you measured 1 voltage using the voltmeter and 1 ampere using the ammeter. Done. So what does it mean if something has 100 ohms of resistance? Come on. What does it mean that something has 100 ohms of resistance? Exactly. It will, if you pass 1 ampere through and you get your hooks and you measure, you're going to measure what? 100 volts deflection. Yes. By the way, everyone, listen up. Just a historical note here to really make you a bit understand the resistance more. Ohm's law, the day he actually discovered it, was not V equals IR. Ohm's law in his own notes 300 years ago was actually this. You know what he did? He built a circuit with a what? With a what? With a battery and some what? And some wire. And he put something what? To resist, like in the middle of the circuit. And then he started doing what? Changing the what? Changing the voltage. So everyone, imagine if this, okay, do you think you can change the voltage of this one, or are you stuck with whatever it says? Or sorry, or whatever you measured? Can you ever change the voltage of this? No. What can you use to have a variable voltage? Ladies and gentlemen, pretty sure you've seen these before, right? These are called what? Power sources. Okay, this one allows you to what? To change the voltage going in. You see what I mean? Okay, again, so this one goes up to what? This one goes up to 0 to 20 volt direct current. It's not an alternating. So this can only what? Pump up as much as high as how much? 20 volts at what maximum current? 500 milliamperes. Okay, we have this one. I don't like to use them though. I actually like to use the batteries. Okay, we have this one. These are all called what? Power supply. Power supply. Power supply. It supplies power, meaning it's a voltage source. Okay, it's a fancy battery you can change. Okay, so he kept doing what to the voltage? Everyone, he kept doing what? Changing the voltage and measuring the what? Measuring the what? The amperage. The amperage through. He found out, everyone, that every single time he changed the voltage, listen up, every single time, look, he changed the voltage, he measured the current, and then he would do what to them? Multiply or divide? No, here. He would divide. Okay, he changes the gain, he measures the current, and he divides. He changes the voltage, he measures the current, he divides. What did he keep finding out? He kept finding out that the R was always the what? Exactly. He always found out that if you pump this up, What happens to this? Come on, think about it. If you keep the same wires and you keep the same resistor by the way, these are how resistors look like. Everyone look, these are how resistors look like. If you keep this one and you keep this one the same, and you just keep using what? A stronger and stronger and stronger battery. What do you expect is going to happen to the current you're able to pass through? Lower or higher? Exactly. So he invented what? He was like, you know what? Let me measure the ratio. Let me see if, you know what, the ratio starts. That's why it's easy to remember what resistance is. Resistance is a what? Is a ratio. That's why it's also called what? Come on, what's the symbol? No, symbol. What's the symbol? R. R, resistance. Also, R means what? Ratio. What's a ratio of two numbers? Come on, when you have a ratio of two numbers, are you multiplying them or dividing them? Exactly. He discovered that as far as increasing this one, what also increased? But in a different ratio or the same way every time? Okay, here's a question for you. What would happen to any circuit if you really go super high with the voltage? What could you do to the circuit? Try it. Why? Because the heat dissipation or the heat loss got to be what? Very high. Okay, imagine if you pass in a copper wire. Imagine if I pass 1,000,000 volts in this. Do you think it's going to be able to handle it? It will what? So it will change from a solid state to a what? Technically, does it? Okay, not technically. Does it still have resistance? But is the resistance of the liquid state the same as the resistance of the solid state? Exactly. He found out that when you change the state, the ratio does not stay the same. Is it making sense? By the way, did we do a state change also in another unit of physics? Come on. What also depends on the state of the matter? Mm, come on. Think energy and work. What depended on specific heat capacity? Ice and water. Do they have the same water? Ice and water. Do they have the same heat profile? No. Which one is easier to melt? Ice or water? Sorry, which one is easier to increase the temperature of? Ice. Why? Because the C for it is 2,100. What's the water? What's the C for water? Does anyone remember? 4,180. Double. You need always double as much heat to heat up water by 1 degree than compared to what? Than compared to the solid state of ice. There you go. Yes. Perfect. All right. Okay. So this is the definition of the ohm. Come on. The definition of the ohm. So everyone, I'm gonna actually just put a couple of resistors on each table because I want to show you something interesting about resistor. Couple randomly chosen. Couple. Okay. Can someone tell me what do you notice about these resistors? What's on them? Like what's on the actual? Forget the two wires on the sides. What's actually drawn on the actual body of the resistor? Say again. Bars of different what? Thank you. Yes, everyone. It's very important to what? Not memorize. It's very important to understand how to what? How to read the color code. The color code of a what? Of a resistor. Okay. Resistor color code. You have to copy anything. I already printed it for you in color too. Oops. I got it. There you go. So I'm going to teach you how to read this. Please keep this on you. Please. I have a budget. Science budget, yes. 6. You got it? Okay. All right. Okay. So everyone, let's. Okay. How do you actually what? How do you actually read the color code? Now, everyone, listen up. So resistors come in what? How many varieties? 2 varieties. Some of them have how many bands? How many? 4 bands. And some of them have how many? 5 color bands. Okay. Tell me what type of resistor do you have? Do you have the 4 color one or the 5 color one? We only have the 4 color one. Okay. So how do you actually what? How do you read it? Now, by the way, it's sometimes the only confusing part probably about reading this is deciding sometimes if it's red or orange, right? Or if it's yellow or gold. Make sense? Or is it gray or silver? I know sometimes it's even hard for me to guess it. So let me show you, for example, one that I have here in my hand. Okay, everyone. By the way, a question for you. Everyone, listen up. So one question is, where do I read from? Listen up. Do I read from this side or this side? Always read from the side. Do you see how one side has more space than the other? Yes. Never read from the side with more space. Read from the side with what? With less space, like the one where the color is closest to the edge. Okay? For example, here, which color is closest to the edge? The red or the silver? Red. Red. So I have to start with red. Okay? By the way, your last color is either red, your last color, your fourth color is either what? No, sorry, not red. Is either what? Gold or. So you know, if you have gold or silver, do not start from there. Start from the other side. So everyone, I have what? Okay, Walid, what do you see? Forget the silver. What do you see? Red, red, black. Okay, everyone. Walid sees what? He sees red. Shh, guys. Red, red, and black. What does that mean? How big is this resistance? He said what? Red, red, and the first color is just the what? Come on. The first color is just the what? First digit. The second color is the what? Okay. We don't have a third digit because this is how many bands only? 4. So you have the first color. You have the second color. So you only have how many digits? And then you have your third one is your what? Multiplier. Multiplier is basically what power of 10 do you use? What power of 10 for black? For black, what power of 10? So everyone. Oh, and what's the last color? Is this gold or silver? Come on. Silver. What does silver mean? You have as much error as what? 10% of your what? Of your value. What does this mean? Everyone, so what's red? Ali, what's red? What's red? What's red? 2. Red is 2, okay? So sorry. Yeah, 2. So 2. What's my second digit? Also what? Also red. So it's 2. And then I need my what? Multiplier. So you multiply times 10 to what? What's black? 1. And then plus minus. Is it gold or silver? It's silver. Silver gives me an error of how much? 10%. Okay, come on. What's 22 times 10 to the 1? Come on. 22 times 10 to the 1. No. 220. 220. Still plus or minus how much? How much is 10% of 220? Come on. 22. What does this mean? This resistor here, yeah, 10%. So a silver error is 10%. Okay. So what does this mean? This one, 10% is how much? Come on, 10% of this. 22. What does this mean? This could not be bigger than what? 220 plus what? Which is how much? 242. And it could not be less than, which is how much? Do you see what I mean? By the way, when we do our lab on Monday, we are not going to care for what? For this. We're always going to just care about the actual number itself. Okay. Okay. Yasmin, what do you have? Come on, let's read yours. What do you mean? No, but look, your last one is gold, so you never start from it. Okay. Everyone, even if it looks like they're what? They're the same edge distance. If one end is gold or silver, do you start from there? No, you start from the other side. So Yasmin, what do you have? What's your first color band? Brown. Okay. Where is brown? Brown is 1. So brown, everyone, brown is 1. What's your second band? Black. You sure? Okay. 10. So sorry, I mean 0. Times. What's your multiplier? What's your third band? Orange. What's our multiplier, everyone? Yeah. So multiplier is what? 10 to the 3 or 1,000. Plus or minus. What's your last band? Gold. What's gold? 5% error only. Half the error of the silver. Okay, what's 10 times 1,000? Come on. 10,000 ohms. Plus or minus. How much is 5% of 10,000? Come on. 5% of 100 is 5. Come on. 5% of 100 is 5. 5% of 1,000 is 50. 5% of 1,000 is 500. That's it. Is it making sense now? This is how we read. Tammy, what colors do you have? Again, do not start from gold or silver. Start from the other side. Orange you have, so we start with 3. Keep going. Another orange. Thank you. Times. What's your multiplier? Sorry, so what's your third band? Brown is 10. And then plus or minus what? Gold is what? 5%. So what's your resistance? 330 plus or minus. Everyone, how much is 5% of 330? Well, I know that 10% of 330 is what? 33. So I need half of that. How much? 16.5 ohms. Again? She said orange, orange, brown. Okay? So does it make sense now how we read the color code? That's how we read the color code. Okay? All right. One last thing before we were done. Come on, 5 minutes. Let's do what? Let's do a couple of demos. Come on. Is this the one you have? Yes? Okay. Oh, yeah, it has on the same page. Okay. A home theater system has a speaker with a resistance of 8 ohms, and it's able to what? To connect to a 5.2 battery or voltage source. What is the current going through? Again, by the way, everyone, how many equations do you know for current now? 2. The one I taught you yesterday, I equals Q over delta T, and the one I used today, which is what? The amazing Ohm's law. Which one are we going to use here? Are you given any charge or time information? But are you given resistance and voltage? We need to use what? Ohm's law. So go ahead and say V equals IR. But I need the I, so what do? V over R. So that's it. You divide 5.2 volts by a resistance of 8. How much is that? Point plus you? Point, how much? 6.5. In what unit? How do you measure current amps? Capital A. Done. Okay, next one. A portable fan is operating at a voltage of 9 Vs. The current going through, 160. What's the small m? Milli, like millimeter, milliliter. Thank you. Determine the resistance. So R equals what? V over I. What's my voltage? Come on. 9 standard volts. How are you? Sorry. How are you gonna write? So 9. How are you gonna write 160 MA? 0.16. What's another way? 160 times. What's the power of 10 for milli? Negative what? 10 to the negative. It's our biggest small scale. 160 times 10 to the negative 3, or as Omar said in standard notation, it would be what? 0.16. So 9 divided by how much? 56.3. In what unit? Its resistance. What's the sig fig? 2 or 3? 3? All right. I don't know. That's 2. Oh, 2. Okay.